All right, very good morning to all of you. I'll begin today's session. Fine. Uh, so today's session we'll start up second module, which is on AC/DC controlled rectifiers. As you know that power electronics is all about power conversion process. The first of the power converter that happens to be, you happen to encounter, that is actually the AC to DC rectifier part. Previous session I had given a very brief introduction on the AC/DC rectifier or the need for variable DC voltage. I said I'll recollect that and then we'll discuss the half wave controlled rectifier. With that, I think from that background, with that background, I think we can pass on to the other subsequent power converters, which are DC to DC and other things at subsequent intervals. Now, you need to understand this. See, power converter is a very broad term, which means this encompasses AC/DC rectifier, DC/DC converter, DC/AC inverter, AC to AC power converter also. All the four power conversion equipments or power converting circuits, power converter circuits, you can call them anyway, they are categorized as power converters. But generally, when we tell converter, then it is going to be AC/DC rectifier, at least in this course. Otherwise, we'll be very specific. So this you need to understand. It is a very broad term. And then if you take AC to DC rectifiers, you might have come across diode bridge rectifier earlier. That comes under the category of uncontrolled rectifier. By now, you know that power diode is an uncontrolled device. Therefore, you will not have the option of obtaining variable voltage, DC voltage at the output. So that comes under, that is diode based. All devices in a bridge, if they are diodes, then it is called as an uncontrolled rectifier. Incidentally, the rectifiers, again, there are various types. You have, based on a transformer, you have midpoint type. Based on the arrangement of devices, you have the bridge type. But I am not, again, power electronics, we are focusing only on bridge type power AC/DC rectifiers, because if you take transformer versions, there are certain disadvantages. Transformer peak inverter rating is going to be affecting. Again, transformer leakage inductance will affect the device, that will be ringing. More importantly, nowadays, the bridge comes in the form of a brick, intelligent power module, IPM, or smart power module, SPMs. Therefore, only bridge configurations are going to be considered. It goes without saying. So, whatever power converter we deal with, that will be only the bridge configuration. Okay. Then, so that is the category. And again, based on the number of phases, AC, they are of two types. You know that, single phase AC and three phase AC. So you do have single phase controlled rectifier, three phase controlled rectifier. So that is also there. And then there is another option, number of devices in the bridge. If it is going to be half of the total number of devices, we call that as half controlled converter, else it is fully controlled converter. So in this course, we will be dealing with single phase half bridge power converter, single phase full bridge power converter, three phase half bridge power converter, three phase full bridge power converter. In fact, half bridge and full bridge, half bridge and full bridge, they are meaningful for more meaningful in inverters, whereas in rectifiers, we call them as half controlled. So single phase half controlled rectifiers, three phase half controlled rectifiers, single phase fully controlled, three phase fully controlled. So four power converters. Again, this concept I think I explained to you in the previous session, fixed voltage, fixed frequency to variable voltage DC. That is what the AC/DC rectifier does. Now, applications very important. We have come across these applications in the introduction part itself. Still, I am repeating this for additional clarity, or you need to get the impression that power electronics is very useful in practice, in day-to-day life, in industries. Therefore, it is worth repeating. They are used in DC drives, because DC drives or DC motor drives in industries, they need variable DC for operating at variable speed at a given torque level. So one application is DC drive. VFD stands for variable frequency drives. So in AC drives or induction motor drives, if you want to vary the speed, then the input to the let's say induction motor, the frequency has to be changed. That is one option. Or the voltage also has to be changed. The AC voltage has to be changed. So we go for what is called as variable frequency drives. go for an inverter. First we rectify, then we invert. So front-end rectifier for variable frequency drives, and then arc furnaces and heating and smelting application, they are used for extraction of metals and recycling of iron. Therefore, you need to heat, and the best way to get that heat is through this electrical energy. So electrical energy is being applied to the control rods, and then they get heated up. Then nowadays there are two more important applications. This represents flexible AC transmission systems and grid integration of renewable energy sources. So I think it's better to write down the two explanations or two expansion, abbreviation of two expansions, and then I will proceed further. This represents or the expansion of this is flexible AC transmission systems. Whereas the other one is, this is variable frequency drives. Sometimes they are also called as variable speed drives, VSDs. But VFDs, it's a more popular term. So these are the applications. I think I had explained this. Of course, half controlled and fully controlled I have explained. Other option is half wave. Only one half cycle of the input is going to be rectified. The other waveform, the other option is to rectify both the half cycles of the AC input. That is also possible. Generally, students confuse half wave and half controlled. They generally get that confusion. Over the years, I have seen that they still get confused. Still meaning, even after completing their degree, they get confused. So please remember, half controlled would mean it is a full wave rectifier. Half controlled is a full wave rectifier, which means it rectifies both half cycle of the input AC. Only difference is half of the total number of devices I will add for clarity in a bridge configuration. They are going to be controllable. That's all. So if you take a single phase bridge, the half controlled converter will use two diodes and two SCRs. If you take three phase, 3 diodes, 3 SCRs. That's all. But it will rectify both the half cycles. Please understand that. Don't confuse with half wave. Please understand that. Now, we will start up with this half wave controlled converter with RL. The basic idea of working with RL load can be easily understood only when we consider the half wave converter, half wave rectifier. That is why I am including this. But actually, if you take your syllabus, it starts with half controlled only. But straight away, if I start half controlled, it will be a bit difficult to understand. Now, the important thing is you need to understand the behavior under the load conditions. When the load has RL, inductance, what is going to be the effect of inductance? That you need to understand. How does the SCR turn off, which is called as commutation, etc. So the configuration is going to contain only one SCR because it is half wave. Right? So let us discuss this. The circuit is given over here. You have the input AC supply, and then the SCR is named as T1. Then the load is containing the R and L. Example of RL load. All loads, in fact, they have a stray inductance component. You can even assume a light, light meaning the fluorescent lamp that has an, of course, it doesn't work in DC, that's one thing. But if you take LED lamp, again, it has got a stray inductance. Or you can take a motor, the armature of a motor, it has got a back EMF also. So that will be RLE load to be modeled in a perfect sense. Or all generic heaters, heating coil is a best example of RL load. Now, why do I say heating coil? Because we know that the out of R and L, R is going to be predominant in the heating coil. Still, there will be a stray inductance. So, what will be the effect of that inductance? We need to understand. Now, remember, if you want to understand the operating principle very clearly, then this condition. The SCR is going to turn off only when its anode current is less than the holding current value. So this option you need to understand, you need to recollect if you want to understand the operation clearly, number one. Number two, the SCR has got various states. I will now go to the next slide and then I'll try to find out whether you are able to answer the question or whether you are able to understand the operation. Fine. Now the input AC half cycle, AC waveform, not even half cycle, input AC waveform is presented here. Now we need to understand for one half cycle what is going to happen, things like that. This is the input waveform. Now when does an SCR turn on? Under this condition, if the input AC supply is provided to the circuit that is given over here. Now the operation is like this. From 0 to pi, the supply voltage is positive. Therefore, SCR T1 will be in forward blocking state at omega t equal to 0. So T1 will be in forward blocking state. So at omega t equal to 0, supply is forward biased. Therefore, SCR T1 will be forward biased, but because it is not receiving a gate pulse, it will be in forward blocking state from omega t equal to 0. This is what happens. Next, when a gate pulse is applied at omega t equal to alpha, SCR T1 will begin to conduct because it was already forward biased. So at omega t equal to alpha, because it is receiving a gate pulse, T1 begins to conduct from omega t equal to alpha. Now this alpha is referred to as firing angle or delay angle. Alright. Now the moment SCR begins to turn on, the moment SCR starts conducting, remember SCR is operating as a switch. So the moment switch is closed, there will be current flowing through the circuit. Therefore, current will start flowing from the supply through the SCR and then through the load, and then it gets completed this way. The direction, the way it is marked. As a result, because supply voltage is positive half cycle, so the same supply voltage will be appearing across the load. Because if you take an ideal SCR, there won't be any voltage drop. Practical SCR, there will be a finite voltage drop. Otherwise, shape of the waveform is not going to change because of the intermediate SCR. Therefore, load voltage will simply be following the source voltage. So load voltage will be same as the source voltage. That you need to understand. Load voltage will be same as the source voltage. Don't put equal, it is actually same. Whatever, that will be same as the input voltage. So because of this reason, we have drawn the output voltage waveform just exactly similar to input voltage. Please note this waveform carefully. Omega t equal to alpha, look at the magnitude at which V naught starts. It doesn't start at 0. Please understand that. It is not starting at 0. It is starting at whatever would be the value at that instant. So you just have to project this, then you will understand the magnitude of the load voltage that at the starting point, to be precise. See, you just have to project this and then see what is the input voltage magnitude. It will not be 0, it will be finite. Alright, so this magnitude is what is observed here. That is a starting point. Why am I stressing this? The reason is if you trigger at 90 degrees, the waveform will start at 90 degrees at the load end as well. And if you trigger beyond 90 degrees, it will start at that instant only. Therefore, load voltage waveform will simply be following the source voltage waveform. That's all. Now, at omega t equal to pi, the supply voltage would have reversed at this point. At omega t equal to pi, the supply voltage just begins to zero, or in other words, supply voltage has come down to zero, to be precise, at omega t equal to pi. Now, because the supply voltage has reversed, the current through the SCR should reverse, but no, it doesn't happen because the energy in the inductance, stored energy in the inductance will not allow the current to decay very fast, because that is a property of inductor. Inductor is going to oppose sudden change in current. At omega t equal to pi, voltage comes down to zero. Therefore, current must also come down to zero, but inductance opposes that current. Therefore, conduction continues even after omega t equal to pi because of stored energy in the inductor. So this portion is due to stored energy in the inductor.
Sir?
Yes?
Sir, can you repeat this point once, sir?
I will write this first and then I'll repeat. See, the understanding t equal to pi, supply voltage is zero, and after omega t equal to pi, supply voltage reverses its polarity just after omega t equal to pi. Now, if we look into the circuit viewpoint, because the voltage has come down to zero, the current would also is also expected to come down to zero. When current comes down to zero, SCR should turn off. This is the expectation, anticipation. However, because of this inductance, there will be stored energy in this inductance. Inductance will not like the current coming from finite value to zero or zero value to change in direction is there, right? Current becoming negative. So the inductor does not permit it abruptly. Therefore, it will force the SCR to continue to carry current in the same direction. Therefore, we get this portion. Did that help you in understanding better?
Yes, sir.
Yes, okay. So this is the effect of RL loop. Whenever we have an inductance, due to that stored energy, current through the SCR and the circuit will sustain for some duration even after the source voltage reverses its polarity. This is the importance of RL, which means at omega t equal to pi, current would be zero, so voltage will be zero because SCR would turn off. That's all. Now, because of inductance, SCR continues to conduct. Fine. Now, one more question. What if the inductance were extinction, meaning when the instant at which the SCR is turned off, becomes extinct. Not physically, of course, it is turned off. That is called as extinction angle. Alpha I have denoted earlier. Anyway, I'll write it here as well. Firing angle. And the duration beta minus alpha is called as conduction angle. So this is what I was referring to. When the value of L is very high, conduction angle will also be more. Conduction duration, conduction angle You can understand that way. Conduction angle will also be more. Of course, given the fact that the load setting remains the same, I am not changing R. Okay, one more understanding. What if alpha increases? You set R value, you set L value. Now you increase alpha. What do you expect? What do you think that will happen with regards to the stored energy if you increase alpha? Meaning you push alpha. What is the range of alpha for this? 0 to pi. That's all. That is the maximum range. Beyond this, SCR will be reverse biased, so you can't trigger. So range of alpha is 0 to pi. I think you can understand that. Range of firing angle or range of alpha is going to be 0 to pi. Now, if I increase alpha, when alpha is increased, of course, for the same RL value, what will happen to conduction angle? Decreases justified. The duration available for the SCR to store energy. See, when you increase alpha, when you push alpha beyond 0 towards pi, the duration that is available for the SCR to conduct and transfer the energy to the inductor, that duration is going to be less. That is conduction angle. Therefore, when the conduction angle becomes less, the duration is going, lesser amount of stored energy will be there. So this portion will also reduce. Conduction angle comes down. You can understand that way. Sorry, I need to just pen and complete it. So these are few points that you need to understand. Now this is what happens. Next half cycle, very clear, because the input half cycle is reversed, SCR will be reverse biased. So you cannot trigger it on. Even if you turn it on, it won't. Even if you trigger it, it won't turn on. This is what happens till beta, and thereafter the cycle repeats. One cycle is complete. So from 2 pi to 2 pi plus alpha, SCR T1 will be in forward blocking state. And then at 2 pi plus alpha, it receives a gate pulse, it begins to conduct, and then same sequence of events happen. So this is how the waveform is going to be. Okay. So the key points are: alpha is firing angle, beta is extinction angle, conduction angle is beta minus alpha. When you have a load inductance, stored energy in the inductor is going to make sure the SCR continues to conduct even after the supply voltage reverses. From 0 to alpha, SCR remains in forward blocking state. Forward blocking state. Okay. Because I have told that I'll tell. From alpha to pi, SCR is in on state. From beta to 2 pi, SCR will be in reverse blocking state. So the state of SCR is 0 to alpha, forward blocking state. Alpha to pi, alpha to beta rather. Alpha to beta, conduction on state. Beta to 2 pi, beta to 2 pi only, beta to 2 pi reverse blocking state, 2 pi to 2 pi plus alpha again forward blocking state. These are the three states of SCR. Okay. Now, what is the principle of controlled rectifier? We need to get variable DC voltage. How do we get variable DC voltage? What is causing that variation? The firing angle is going to cause that variation. Now, how do we quantify that firing angle, or how do we quantify the amount of average output voltage obtained across the load? We will try to derive the expression for average output voltage from basic principles. See, we are given a waveform. So all that one has to do is we need to find out the value by using simple integration principles over one cycle. So V0 average is given by V0 average will be given by from basic principles. It will be 1 by time period, integral 0 to time period, which is 2 pi in this case. Whatever value of output voltage I get, V0 of omega t. For clarity, I will write this as V0, but omega t is here, so it's a function of omega t, d of omega t. That's all. Okay. Now, looking at the waveform, I will substitute the limits as follows. From 0 to alpha, the waveform is 0. From alpha to beta, the waveform is this portion. I am referring to this portion, alpha to beta. It is just a sine wave. Okay, and the time duration is alpha to beta. This is alpha, this is beta. So alpha to beta, it is Vm sin omega t. Whatever waveform I have here, that's a sine wave. So I express that as Vm sin omega t, d of omega t. And one cycle is not over. I started off from 0, I should end at 2 pi. Or I have started from alpha, I should end at 2 pi plus alpha. Anything is fine. I will write from beta to 2 pi. The magnitude is 0. That's all. So do that integration, simple integration. You will get Vm by 2 pi into integral alpha to beta sin omega t. So once you complete this, you will get the average output voltage expression as Vm by 2 pi into sin alpha integral, sin omega t. You integrate, you get cos omega t minus cos omega t rather, minus cos omega t. And then minus cos omega t, you have to substitute the limits. Therefore, you will get cos alpha minus cos beta. After you carry out the integration and substitute the limits. This is how the output voltage expression is varied. We vary alpha, therefore by adjusting alpha, beta you can't adjust because beta depends on the load parameter and the firing angle. So by adjusting the firing angle alpha, V0 average, or I will write variable DC voltage is obtained at the output. That will be even more meaningful, easier. Variable DC voltage is obtained at the output. That's all. So this is the way we obtain variable DC voltage from a fixed voltage, fixed frequency AC input. Now, where can the half wave controlled rectifier be applied and why? See, because we are not rectifying the other half cycle. See, the negative half cycle is not rectified. Therefore, we are actually missing out a large amount of power that is being available at the input. So power conversion is not going to be that much. We are just wasting 1/2 of power that is available. So it is used for very low power applications. It is used only in low power applications. It could be heating application, like heating. Don't think of heating and smelting in terms of megawatts. No. They need full wave rectifiers, fully controlled full wave rectifiers. Fully controlled itself means full wave. I know that, but you should know that. So very small heaters, power rating till 100 watt, 200 watts, there you can use this, because even if 1/2 cycle is not going to be available, the heat is not going to come down drastically because of the inertia. So for very low power applications, half wave controlled rectifier can be used. That's all. So this is the way. You can of course take up some numerical example based on this and find out what is the average expression for average output voltage. So and this is the waveforms which have been obtained by simulating with these specifications. I have simulated a 250 watt half wave rectifier at 0.8 power factor lagging. Firing angle, I had taken that as 45 degrees. See, this is for two purposes. Number one, to understand the effect of RL load. This is the RL load behavior that we have seen. We had discussed this in theory. And main thing is, this is the way you have to present your simulation results. Operation wise, we understood that when the stored energy in the inductance is there, as long as stored energy is there, conduction will be there. Now, if you try to correlate this, you will understand that only when the load current falls down to 0, the SCR current falls down to 0, and then the voltage across the load falls down to 0. So this sort of correlation is what is needed from students. This exploration is left. You don't expect me to tell these are the waveforms that are required. No, your understanding is what matters, especially in lab and when you get simulation based things. Okay, so that part, that is very, very important.